Welcome back to the course on superconductivity. Today we're going to talk about enthalpy margin. We'll first do a small recap about stability and its parameters, then we'll define the enthalpy margin. First of all, the definition of stability is the ability of a system to withstand perturbations. In our case, it means the ability of a magnet to stay within this triangle, defined by the critical current and the critical temperature. At a defined temperature, we have a range to choose from for the operating current. Nowadays, the operating current is usually around this range. The top end being the riskier but economical, and the bottom end being safer but less economical. The disturbances that we talked about earlier will drive the magnet towards the limits of the triangle or even out of it. Taking back our triangle, let's define the operating point right here. If the magnet temperature increases a bit, we will enter the current sharing region that we defined in chapter 5.1.2, where this amount is going to flow in the matrix, so resistively, and this amount in the superconductor, so superconductively. Going back to the operating point, we can see that we have a margin in operating current, and a margin in temperature before going to the current sharing regime. That's what this temperature margin that we will define the enthalpy margin. Now, just to remind you, for some magnets, it is still fine to be in the current sharing regime if they are cryostable. However, the enthalpy margin is defined so that it is safe even for adiabatic magnets. So, the enthalpy margin is defined as the amount of energy necessary to drive a magnet or parts of it into the current sharing regime. In other words, it is the amount of energy needed to heat up a part of the magnet from the operating temperature to the current sharing temperature. It is therefore defined by the integral, from top to TCS, of the specific heat capacity of the magnet. In the table on the right, some orders of magnitude of specific enthalpy margin are given for LTS and HTS superconductors. The main idea of this table is to show that HTS are in general much more stable than their LTS counterparts due to their large enthalpy margin. This graph shows orders for the energy density and the timescale of several disturbances. Here, we have a few disturbances that we learned about before, but also particle showers and nuclear heat. Particle showers happen in particle accelerators when high-energy particles interact with dense matter. Nuclear heat is, as the name suggests, the heat generated inside nuclear reactors. On the right-hand side of the graph, the typical enthalpy margin of LTS and HTS is referenced. To conclude, by definition, the enthalpy margin is the amount of energy needed to drive a magnet or a part of it from its operating temperature to the current sharing temperature. It is a useful value that can be used as a reference when working on the stability of a magnet.